Okay, welcome back to this session on avatar perception. Thank you for joining. We're going to have 5 different papers. And the first one is going to be by Keigo Matsumoto, Detection of Thresholds for Vertical Gains in VR and Drone-Based Telepresence System. Remember that you can send questions all the time through the what's the name again? Slido, sorry. And I'll be moderating and then asking the questions to the presenter. Okay, Keigo, thank you for presenting.
Thank you for the introduction. Let's start.
Hello everyone, I'm Keigo Matsumoto at the University of Tokyo. These videos are represented our studies. The video on the left shows the application of vertical gain when crouching in a VR system, and the video to the right shows the application of vertical gain when stretching in a drone-based telepresence system. Here is the outline of my presentation. First, I will introduce the background. Then I will talk about research aims. Thirdly, I will mention related works. Then I will introduce vertical gain. After that, I will describe user studies in a VR system and a drone-based telepresence system. And lastly, I will conclude with take-home messages. Background. There are many vertical motions in VR and telepresence systems, such as jumping, stretching, and crouching. But these vertical motions have not been well studied. If you apply real movements directly to VR or telepresence movements, the range of motion and the accuracy of the motion are limited. To solve these problems, we proposed vertical gains. By introducing vertical gains, we can extend their vertical movement in VR and telepresence systems. We also verify the detection thresholds of vertical gains in both systems. Let's talk about related works. A technique called redirection that extends horizontal movement in VR has been studied for more than 50 years. Redirection makes it possible to explore a first virtual environment on foot in limited real space by shifting the correspondence between real space and virtual space. In particular, a technique called translation gain makes it possible to manipulate the walking distance without the user's notice. Another technique called redirected jumping that applies redirection vertically has also been proposed. In the redirected jumping, the distance, height, and rotation when jumping are manipulated. There is also research on drone-based telepresence systems using motion gains, but these studies only applied 1.0 and 2.0 gains in vertical and horizontal directions at the same time, and did not investigate detection thresholds. Let's move on to vertical gain. Vertical gain is defined as the delta virtual height over the delta real height, or the delta remote height over the delta local height. In a VR system, vertical gain under stretching and crouching works like this. On the other hand, in a drone-based telepresence system, vertical gains work like this. Next, I will talk about the first user study, vertical gains in a VR system. Here are the equipment and environment used for the experiment. We used an HTC Vive and we prepared the virtual environment, which looks close to the laboratory environment. We gathered 17 participants from a local campus. We used SUD2 Alternative Fourth Choice, 2AFC, Simulator Sickness Questionnaire, SSQ, and iGroup presents questionnaire IPQ. In this presentation, I will explain only SUD2AFC. For details of SSQ and IPQ, please read our paper. We did 84 trials per participant. 7 gains, 2 to the power minus 1.5 to 1.5 in 0.5 increments, 6 repetitions, and 2 conditions, stretch and crouch. Under stretch condition, we apply vertical gains while the user is standing on the toe from a natural standing position. On the other hand, under crouch condition, vertical gain is applied when the user crouches down from eye height to 90% of eye height. These videos are represented vertical gains in VR. The video on the left shows the stretch condition and the video on the right hand shows the crouch condition. The SUD2AFC is displayed when the user stretches or crouches, and the user answers the questionnaire using their controllers. Before explaining the result, I will explain SUD2AFC briefly. In SUD2AFC, the user compares the actual movement with the virtual movement. Then the user has to answer whether the virtual movement was larger or smaller than the actual movement. This figure shows the percentage of virtual movements reported as larger than actual movements. The horizontal axis shows each gain, and the error bar shows the standard error. We approximate this pooled result with the logistic psychometric function shown on the right. Finally, we define the point at which the proportion of responses is balanced as the point of subjective equality, PSE. The PSE indicates the point where the actual movement matches the virtual movement. We also define the point where the proportion of responses is 25% and 75% as detection thresholds, DT. In the field of redirected walking, users are unaware that the gain is being manipulated between 25% DT and 75% DT. So these figures show the result of SUD2AFC under stretch and crouch conditions. Here is a summary of the results. Focusing on PSE, since the value of PSE is larger than 1, it can be said that the vertical movement on VR is evaluated as smaller. This is probably because the field of view and the environments are different from reality. Focusing on DTs, the stretch threshold was wider than the crouch threshold. This is probably because the amount of movement and stability are different between stretch and crouch conditions. Next, let's compare our result to farmer studies, jumping height relocation gain and translation gain. Comparing the vertical gain under stretch conditions and the jumping height relocation gain, the vertical gains PSE and DTs were larger. Compare the vertical gains and the translation gain, the range of vertical gains DTs were wider. Let's move on to the second user study, drone-based telepresence system. Here are the equipment used for the second experiment. We used a Telo drone with wide lens, which has 100-degree FOV. These videos are represented vertical gains in drone-based telepresence system. The video on the left shows the stretch condition, and the video on the right hand shows the crouch condition. We gathered 12 participants from a local campus. The experiment was performed under the same conditions as the VR environment. These figures show the result of pseudo-2AFC and stretch and crouch conditions. The value shown in red is a reference value because it exceeded the gain range used in this experiment. Focusing on PSE, since the value of PSE is larger than 1, the vertical movement on Treplezan system was evaluated smaller as well as virtual condition. Focusing on DTs, the stretch threshold was wider than the crouch threshold, as well as the virtual conditions. Next, let's compare the result of the Treplezan system to the result of the VR system. Comparing the vertical gains under the Treplezan and VR system, the PSEs and DTs of the Treplezan system were larger than those VR system. This is probably because the latency of the drone. The delay may have caused the users to move more than the drone. Focusing on the DTs, the range of DTs under the Treplezan system were wider than those VR system. This is probably due to the narrower FOV. Conclusion. From our two user studies, we revealed that vertical movement in VR and Treplezan systems are evaluated smaller, and that DTs are different between stretch and crouch conditions. And also, the range of DTs of vertical gains are larger than those translation gain. In the future, we hope to solve the problems of drone latency and FOV for more accurate evaluation. And we also want to evaluate applications that apply vertical gains. Here's our take-home messages. Thank you for listening.
Okay, so we have some questions already, and people can still send more questions on Slido. The first question by Bernard Ricke is, do you have any feedback from the users when they were using noticeable vertical gain factors? Was it strange, annoying? There was sickness inducing? Could they still be used if needed?
Okay, so from the users' free discussions, they said, most of the users said it's like a funny experiment. So I think they didn't, it was strange or annoying, but much more enjoying, I think.
Okay, so they didn't get a particular motion sickness or?
Yes, from our user studies, SSQ score is not going up very much, so I think so.
I guess the first person control, it's very important. Okay, so we have another question by Andrew Best. Do you believe the scale of the virtual environment in study 1 would affect PSC? Was the scale of objects in your study consistent with the real world?
Yeah, I think so, because in the virtual environment, usually the scale of the size is perceived smaller than the real world because of the FOV, and also the quality of the object is different. So yeah, in our experiment, the results are very similar to the horizontal gains. So I think that's so.
Okay.
Scale of the yes.
I have another question. Is in general this type of controlling through motor actions? Do you think it is much better for vestibular system than just having a joystick or something like that, which is what usually it's being used for controlling drones? What's your view?
Okay, for application for entertainment, our system are useful, and other things like inspection, or if you inspector want to move like a 3D motions, it is very difficult to control the drone by joysticks, especially for not matured controllers. So yeah, I think our system is a very intuitive.
Okay. Okay, sounds good. So there are no more questions right now, and I think we are going to prepare the next talk.
Okay.
So the next talk is by Brendan John from University of Florida. We are in the session of Avatar and Perception, session 4, and you're welcome to send your questions throughout the talk through Slido. The talk is the security utility trade-off for iris authentication and eye animation for social virtual avatars. Thank you, Brendan.
All right, so hello everyone, I'm Brendan and I'll be presenting today. So originally, I didn't plan on giving this talk remotely. However, due to a global health crisis, here we are running IEEE VR in virtual reality. And this brings to focus some of the work I've been doing lately, because I had to choose between presenting over Zoom with a webcam, like I'm doing now, where you get to see some of my rich, nonverbal social cues and gestures, or to present using Mozilla Hubs, where we get a sense of social presence in a shared virtual space, but we give up some of these subtle cues. So we as a VR community know that we shouldn't have to choose between the two. In the future, we're not going to have to. So let me play a video from Facebook Reality Labs where I'll be an intern this coming fall.
What do you do for exercise?
I do yoga and then I do boxing too.
What kind of yoga? Wait, okay, yoga and boxing.
Yeah, there's a nice.
So we can see that the future is quite rich, and the eyes play a critical role of this, which means we need to start using eye tracking technology. And as more individuals use this type of technology, we're actually exposing them to a very simple security vulnerability. And that vulnerability is the fact that the iris pattern seen here is imaged by eye tracking cameras. And this pattern is actually a gold standard biometric. So we have a very simple threat model in this work. We assume that you don't trust the eye tracking platform or system. What this means is that the HMD or the network you're using to send data for processing could be compromised. We assume that an adversary wants to steal your password, essentially your iris biometric, and spoof your login info. So for example, say the adversary has access to the data port used to transfer the images, they can log these images, turn around and use them to log into your account. And while this hasn't happened yet, hypothetically it could with the Microsoft HoloLens V2, which enables iris authentication from the eye tracker to log into your Microsoft account. So this is a feature, but it's also a huge security vulnerability because we're essentially streaming your password in plain text at 60 frames per second, which is not good. So of course, there's some related work in the area. In terms of AR, there's studies into the malicious inputs and outputs that might have a negative effect on the user, such as rendering an object suddenly to make the person trip and fall. There's work in wearables and the privacy of bystanders. So you saw this when Google Glass came out, and a lot of restaurants banned the technology. There's also work in eye tracking, so the privacy of the scene camera, which is similar to the wearables case, as well as publicly released data sets that have aggregate data, and they claim to be anonymized, but in fact still have individual identifiers. So then we have our prior work presented at ETRA 2019, where we presented a solution to secure the iris biometric within eye images, like you saw on the last slide. And in this work, we had a slightly different threat model. We assumed that you could trust the eye tracking platform itself, but that you didn't trust the third-party applications that you gave the raw eye image stream to for processing. So broadly speaking, our research problem is how might we transform the eye image to turn off the biometric and secure our iris signature? So the insight we had in the past worked was simple. The features used for eye tracking and the features used for iris authentication are separable in the frequency domain. So what I mean by this is that the actual pixels in the image that represent these regions, so you can see the iris in this plot is a spiky little section up and down, the pupil is dark and flat, and the glint, the corneal glint, is a Gaussian looking bump. The eye tracking features are low frequency components, while the authentication features are high frequency components. So the actual solution is simple. If we use a low pass filter, we let in the eye tracking features, so eye tracking can still be done, but we filter away the iris signature itself. And of course, in the paper, we have a more theoretical basis for how this works and is implemented. Now, what our key insight was for this work is that we can actually do this in hardware using optical defocus as the low pass filter. So what you see here is a typical eye tracking setup. And on the left, you'll see that the eye camera used to capture the images is quite close to the user's eye. Our invention is to say, simply move that camera farther away to add blur and optical defocus. What we see is that in these configurations, the iris pattern goes from being imaged to being blurred away. And we can still do eye tracking with this type of secure out of focus configuration. And it's easily reversible and controlled by the user, which is very, very important. So our first contribution is to say, for this type of configuration, how much blur is the right amount of blur? So on one hand, we can of course have no blur. We'll have excellent gaze accuracy. So we have a gaze error of 1.4 visual degrees. However, we have a high CRR, which stands for correct recognition rate. Essentially, this is what percentage of frames from the eye tracker could be used to authenticate you as the user. So 79% means about 4 out of every 5 images could be used to authenticate you. On the other extreme, we have too much blur. And you'll see that I've quantified blur with a parameter sigma in terms of pixels. So in the paper, we present a method to map the camera distance in millimeter to this blur parameter. But what we're seeing here is that we blurred the image too much. We can't even do eye tracking anymore. However, we were able to secure the iris biometric completely with a CRR of 0%. So we propose somewhere in the middle, there's a sweet spot around sigma equals 3 pixels, where you still get reasonable eye tracking. So the gaze error is 1.9 visual degrees, but we've drastically lowered the correct recognition rate down from 79% to 5%. So to actually evaluate our configuration, we recruited 15 participants, had them use both configurations, and perform an eye tracking task. On one hand, we looked at security. So the y-axis is the correct recognition rate. Again, how many percentage of frames could be used to authenticate them. And the x-axis is the amount of blur that was added from that secure configuration. So you see a gray cross for each individual, and that as we get to higher levels of blur, the correct recognition rate drops. And after sigma equals 3 pixels amount of blur, the recognition rate is below 5%. On the other hand, we still care about utility and applications of eye tracking. So we studied this in terms of a target viewing task and computed for 5 different targets on screen what was the gaze accuracy and the amount of error. So again, you'll see the gray crosses, but you'll also see gray circles. So this stands for the ideal configuration, so the in-focus, insecure configuration. So to compare them. And we're seeing the errors aren't drastically different in the secure configuration. And we're still bounded above by 3 degrees visual angle, which is quite reasonable for a lot of eye tracking applications and tasks and studies. So our next contribution is to think about this in terms of social VR. So sure, we've quantified the amount of error that we introduce with a secure configuration, but does this have an impact on the naturalness of the eye movements? So social characteristics are a big part of that social VR interaction. We want to retain them when we're using a secure eye tracking configuration. So our next contribution is to look at a few perceptual studies with virtual avatars. Our first research question was to say at what level of blur do viewers even notice a difference in the animation of avatars' eyes when we're using eye tracking data? And we do this by using a detection threshold and point of subjective equality. We essentially compare unblurred eye images that generate an animation with blurred secure eye images that generate an animation. And the second research question in the second study is to say, okay, if you do notice a difference between the eye animations, does it actually degrade your social interaction? Because there's a lot of cues that are based on eye movements, like naturalness, truthfulness, attentiveness of the avatar. And if they get degraded by it, we have to know that as part of the secure configuration. So to actually generate the stimuli, I simulated having a conversation and I tracked myself. And what I did is I watched an English as a second language video where I was given English phrases and time to repeat them back. So simulated conversation. We took this gaze data, put it through an animation pipeline, and animated a virtual avatar, which you can see here. And you'll note that the avatar is not very cartoony or stylish, but it's actually somewhat realistic. We did this on purpose because we know the more accurate that an avatar looks, the more accurate the subtle cues of the eyes must be to have a natural looking avatar and a realistic avatar that doesn't look creepy or put off the social interaction. So then we took all the eye images we collected and systematically blurred them with a Gaussian kernel of different values, and so different values of sigma. We then took these blurred eye images, passed them again through the eye tracking pipeline, and used them to animate the avatar once again for comparison with the unblurred references. So what you're seeing here is similar to the stimuli that participants would see in our first study. What we did is something called a same difference study. Essentially, we played these videos side by side, so each was a different animation, and they had to say whether the animations were the same or different. So let me play the video for you. So focus on the eyes of the avatar, please. Okay, so for the animation on the right, it was actually animated using eye images that were blurred with a kernel of sigma equals 5 pixels. And the unblurred eye images were used to animate the avatar on the left-hand side of the screen. So participants in the study saw more than just one trial per level of blur. We actually had 6 different animations, 5 different levels of blur, and then 2 different orientations. Essentially, we could swap whichever side that the blurred eye images generated in animation were put onto. So again, our method was to recruit 20 participants and perform the same difference study. Over 60 different trials, we collected their responses. So what you're seeing here is a psychometric function. Essentially on the x-axis, we have the level of blur that was used to generate the stimuli. And on the y-axis, we have the same percentage. Essentially, what was their answering rate of same? And what we've done is essentially generalize this in a function that says, for a given level of blur, what's the probability that a viewer is going to notice a difference in the avatar's eye movements? So we study this with a few things. Like you saw earlier, the PSE, or the point of subjective equality, is the same rate as chance. So essentially, viewers are answering at 50%, and they're guessing between same or different in their responses. The next thing we look at is an actual detection threshold. Essentially, at what point are viewers consistently noticing a difference? So in this case, a same rate of 25% means 75% of the time there's telling us they perceive a difference between these two animations playing side by side. And going back to security, our point of subjective equality was at sigma equals 3.5 pixels, where we had a correct recognition rate less than 5%. So our detection threshold was actually at sigma equals 5.6 pixels, where we had a correct recognition rate of less than 2% from our previous data. Okay, so we know there's a point where you're beginning to consistently notice a difference between the animations, but does it have a negative impact on the actual social interaction that you're having? So to study this, we recruited 19 different participants, so they hadn't done study 1 or seen these avatars before, and we showed them individual animations of the avatar. So for no blur and the different levels of blur that we used before. And we asked them statements that they had to respond to, such as, the avatar was truthful. They then had a 5-point Likert scale response from strongly disagree to strongly agree, and they had to do this for each level of blur and each stimulus. We tested 5 different characteristics. So the first was truthfulness, then naturalness, attentiveness, comfort, and eye contact were all asked about after each animation. And what we're seeing is, as expected, for higher levels of blur, these social characteristics degrade. So you can see after sigma equals 3 and sigma equals 5, the median value of these box and whisker plots starts to come down. So thinking about this in terms of social VR, it could be a conference presentation like I'm doing now. It could be a virtual job interview, like you want a new job, or it could just be chatting with family and friends. Two characteristics we might care about are the attentiveness and the truthfulness of this interaction. So our takeaway from these results is pretty clear. There is a change in these perceived attributes after sigma equals 3 pixels. And coming to security, we know there's less than a 5% chance that if someone takes your iris image after sigma equals 3, that they're going to be able to log in with you and steal your identity. So ultimately, we have to recommend a blur kernel somewhere between sigma equals 3 and sigma equals 5 to retain some of this social interaction, but to also add security to the eye tracking technology that those are using. So to summarize our research question, our first takeaway is that we can use defocus or blur to remove the iris biometric from these images. We can do this in software using Gaussian blur, or we can do this in hardware using optical defocus like we did. And this can be applied to several VR and AR trackers that are out there today. Some of them you can adjust the distance, but some also have an adjustable lens. Most importantly, though, the blur parameter, the level of security, has an impact on our applications. So in this case, we studied social VR, but in reality, we want to look at this for different applications like foveated rendering or gaze-based interfaces as more and more VR and AR research comes out. So of course, our work has some limitations. In the study itself, we only animated the eyes of the avatar, which meant there was no blinks, no changes in pupil diameter, and no mouth movements. So naturally, as future work, we want to conduct more perceptual studies to investigate the cues. But we also want to run this in an immersive VR display, as right now we're setting them in front of a computer monitor. There's also some limitations in our security framework. We've made the assumption that you can actually adjust the focus of the camera itself, which is not true for several VR and AR trackers that are out there today, which are housed inside the HMD or using a different system. So as future work, we want to generalize this framework so we can instantiate it with different eye tracking configurations. And last, and something I think is very important, is we've recommended a sweet spot for a fixed iris authentication and fixed eye tracking system or application. In reality, new systems are coming out. So we used a standard iris authentication method. However, month by month, a new deep network could become the state of the art. So what we want to do is generalize this as an adversarial learning problem and present an optimization framework. So given a certain authentication system and a certain utility application or eye tracker, you could automatically optimize and find this blur parameter. That is the sweet spot that we're talking about here. So that about wraps it up. Thank you for your time. I'd like to recommend that you read our paper and visit our website for some more details. And I'd also like to acknowledge NSF for funding our work. Thank you, guys.
Thank you, Brendan. Are we live? Okay, great. So we are now ready to go for the questions. Remember that you can add questions on the Slido. We already have the first question here by Diane Hosfeld from Mozilla. Hey, eye tracking has privacy concerns beyond the iris biometric. Could techniques like this be used to protect other eye tracking derived data that allow interfaces into data like user age, race, gender, affective disorders?
Yeah, so that's a great question. So obviously the iris is one part of the security, but also the eye movements themselves, like you said, can be used to identify some of these characteristics. So something that we've thought about, different than a filter, but there's approaches that use noise. So there's a concept of differential privacy. So you can add noise to these types of gaze data streams, whether it's an aggregate public data set or just an individual. So if I'm adding noise to the gaze stream, you still may be able to use it for some of your applications. It won't be as exact as the original system was, but you might be able to muddy and cloud some of these other personal identifying features, depending on what they are.
Okay, nice. Another question by Andrew Best from Toyota Research. I'm unfamiliar with eye tracking in HMDs. Is the distance needed for your Sigma 3 pixels feasible with current HMDs? What is the value of the total distance at Sigma equal 3?
Yeah, so I don't have the exact millimeters offhand, but what we built this is with a Pupil Lab system. So they actually make a similar system for augmented reality. But what we did was we essentially dragged the camera as far as we possibly could. So this distance reasonably could be implemented with another Pupil Lab system. However, I think what you're pointing out is that a lot of them have different form factors, configurations, so it would depend on the system. The other note is that sigma value depends on the field of view, the resolution, and the quality of the camera itself. So for a different configuration, those parameters also might change, so that the actual distance you have to change might be different for a different configuration.
I have another question which might help on deploying at large on things that are already out there is like, how much of what you have built you think it could be done by software? You know, like instead of having to move the hardware, just applying a filter into the software before you transmit this information.
Yeah, so that has a bit to do with the threat model. So if we're assuming we can't trust the system, that's when hardware comes into play, where the user wants control. But if there's some sense of security that I know someone's not going to hack into my hardware, I'm not streaming it unencrypted over a network, you can certainly make a plugin that adds Gaussian blur as part of that pipeline. So you just take the raw image out, apply this in blur, or apply that blur in software and pass it down the pipeline. Yeah.
Okay. So I don't think there are no more questions right now. Thank you very much for your talk, Brendan. Very cool research.
Thank you.
Okay, our next speaker is Kei Tsuchiya from the University of Electrocommunications in Japan. And he's going to be talking about an optical design for avatar user coaxial viewpoint telepresence. Remember that we can receive questions through the talk on Slido. Thank you, Kei.
Yeah. Thank you for the introduction. So I'm Kate Tsuchiya from the University of Electrocommunications. So I'd like to start my presentation entitled An Optical Design for Avatar User Coaxial Viewpoint Telepresence. So first of all, let me introduce our system easily. So we designed a mid-ray imaging system for telepresence. It can capture audience from the mid-ray avatar's viewpoint. So as background, a CG avatar is used for attractions such as Turtle Talk at several of the Disney theme parks and the VR platform such as Hubs, here we can choose our appearance without any physical restrictions. So I mean, we can change ourselves into any characters. This is an advantage of the CG avatar. In fact, some studies have shown that the avatar's appearance influences to the communication. However, this is only possible in VR space. So we believe that the next step is to extend it to real space. Then our purpose is realizing communication through the CG avatar in real space. To do that, we propose a method taking the avatar from VR space to real space with mid-ray imaging technology. Next, I'll talk about the related work. There are three topics: mid-ray image, telepresence system, and optical transfer of the camera viewpoint. At first, I'll introduce the mid-ray imaging technology. There are various methods to display CG characters for the interactive system. One of them is displaying on the screen. This method displays the CG character only on the screen. On the other hand, the mid image is a real image formed in the air. So we can display the CZ character in real space. To display the media image, we use an optical element called MMAPs, stand for micro mirror array plates. Using this, the media image is displayed at the symmetrical position of the light source with respect to the MMAPs. So we use this element for our system. Second, I'll talk about telepresence system. Various types of telepresence system has been proposed. And one of them is VR and AR-based systems such as Minimi. In this system, AR user can see the CZ avatar using see-through HMD in real space, and VR user plays the role of that avatar in VR space. So the users in VR space and real space can be connected, but the VR user still needs a VR space. Also, there are many systems using a robot. They realize real space interactions through the robot. Let me show you the comparison of the telepresence systems in terms of communication space and the avatar. In VR systems such as House, the users communicate in VR space through the CZ avatar. In the VR and AR-based systems such as Minimi, the communication spaces are VR and real space, and this uses a CZ avatar. The robot system allows users to communicate in real space through the robot. Our proposed system uses a CZ avatar like the VR or VR and AR-based system, and the communication space is real space like a robot-based system. Thirdly, I'll explain about the optical transfer of the camera viewpoint. There is a previous work that transfers the camera viewpoint using MMAPs. Media camera means transferred camera, and it doesn't have a physical body. So it can go through a gap or mesh. A concave lens is also used for adjusting the focal point. Our system is based on this design. All right, next, I'll talk about the principle of our system. Here, I'll show you the optical design. Requirements of these systems are displaying the media image and transferring the camera viewpoint. So it consists of a display, camera, concave lens, beam splitter, and the MMAPs. The light from display is reflected with beam splitter, and that virtual image is D dash. D dash overlaps the camera. Then MMAPs form the media image with the light from D dash and transfers the camera viewpoint to form the midway camera. And we implemented an experimental prototype. We used the DSLR camera and the mobile device as a display. Also, the transmittance of the beam splitter was 50%. Then we conducted some experiment for the evaluation. We assume that the evaluation can be broadly divided into several parts. A basic part is applicability to telepresence. And the next step is evaluation of usability like audio, visual, and so on. Then the final goal is productization. This time, we evaluated the applicability of to telepresence. In this evaluation, we had two unknown parameters. The first one is the effects of the MMAPs. This means how do MMAPs affect the capturing performance? The other is camera setting. This means what camera setting is appropriate for this system. At first, in evaluation 1, we confirmed that there are three effects of the MMAPs: straight light, brightness decay, and blur increase. Straight light means the light that does not form a media image in an optical system using the MMAPs. It appears on the left and right of the media image like this. This is also generated on the captured image in case of camera viewpoint transfer like this. In this area, the image cannot be captured properly. Then we conducted an experiment to evaluate the brightness decay. In this experiment, we measured the luminance of the light source display and the media image. It was measured by a luminance meter from several angles, 10 degrees to 60 degrees. And the display was placed in two patterns, horizontal and vertical. I'll show you the results. The horizontal axis is the angle and the vertical axis is the luminance ratio. In this system, the MMAPs are arranged at an angle of 45 degrees. So it is expected that the brightness is reduced to 40% or less. Next, we conducted an experiment to evaluate blur increase. In this experiment, we measured MTF that indicates the sharpness of the image. Each image was displayed on the display, and it was photographed under two conditions, normal and MMAPs. Normal condition used the camera alone, and MMAPs condition used the transferred camera by MMAPs. Here is the result. The orange line is normal condition, and blue line is the MMAPs condition. As you can see, the value of MMAPs is lower than the value of normal. So this means the blur is increased by the MMAPs. To summarize evaluation 1, we confirmed that the MMAPs cause 3 effects. First one is blur increase, and second one is stray light. This affects the overall brightness ratio of the image. And third one is brightness decay. This can be solved by adjusting the camera setting. So based on their effects and evaluation 2, we will find the design guidelines of our system. Okay, moving to the next part, I'll explain the evaluation 2. Here, we conducted the face detection experiment to verify the camera setting. And the purpose of this experiment is to find the appropriate camera setting for telepresence. We assume that the user needs a quality image to recognize the face to communicate each other. In preliminary experiment, we tried to use a face detection program. At this time, the face detector is not robust enough under the environment we tested, but humans are good enough to recognize a face in such an environment. So we assume that if face detection works on the quality of the captured video, people can recognize faces and communicate using the same video. And we use the face detector for the evaluation too. Also, in preliminary experiment, alt ISO sensitivity setting didn't work. We guessed this is due to the brightness decay, one of the effects of the MMAPs. So we investigated the appropriate ISO sensitivity setting for face detection. In this measurement, we measure the face detection rate under two conditions, normal and proposed system. Proposed system condition use the MMAPs and the beam splitter. The participant was 1, and during the measurement, the participant moved their face and mouth like this video. And we measure the number of detection frames in 300 frames and under 11 conditions of the ISO sensitivity. And I'll show you the results. The horizontal axis means ISO sensitivity, and EV stands for exposure value. And the vertical axis means the detection rate. EV0 means an appropriate exposure under normal condition. In the case of this setting, detection rate is maximum under normal condition. As for proposed system condition, there are 3 settings that exceed the maximum of normal condition. They are settings of 4 to 16 times the appropriate exposure. This means they are appropriate settings. From 2 evaluations, we found 3 design guidelines. First, brightness decay can be solved by adjusting the ISO sensitivity. The adjustment is to set the ISO sensitivity to 4 to 16 times the appropriate exposure. Secondly, blur increase doesn't affect influence to face detection because the maximum detection rates are comparable between the two conditions in the face detection experiment without any measures against blur. Thirdly, straight light reduces the effective angle of view. So this system is suitable for use in an environment where there is no subject on the left and right sides of apparatus. And next, I'll introduce the application. The system design is shown in this figure. The positions of camera and display were switched, and 2 motors were added to control the camera gaze direction. Also, the captured video is displayed on the HMD, and the camera gaze direction is controlled based on the data that the HMD measures the user's head movement. Then we implemented that. We used 2 compact cameras for stereoscopic view, and the gaze direction is controlled like this video. So the user can see the audience from avatar's viewpoint and also look around like this video. Also, we demonstrated this application at CVRF Asia 2019. At this time, we confirmed that users recognize the user audience's face. In conclusion, we showed 3 contributions. First one is that we designed an optical system superimposing the viewpoint of the avatar and camera. Second one is that we evaluated the applicability to telepresence, and that results show that it can be applied for telepresence. And we also found design guidelines. Third one is that we implemented an application for telepresence. This is all for my presentation. Thank you for your attention.
Okay, thank you very much. We'll move directly into questions. Yep. Please go to Slido to introduce more questions. I have a first one. It's very nice that you can reduce the cameras for recording and transfer the information through lenses and mirrors. And do you think this could be also, like currently you had it for an view of people viewing, for example, the holograms, but I could imagine you could miniaturize it to be inside HoloLens or inside HMD to be able to see what the face looks like, you know, sort of like having a system that is further embedded to the face. So right now you're trying to transfer what other people are looking at into the HMD. I'm wondering if you could transfer the HMD is seeing to another HMD. You know, I don't know if you think that could be a possibility.
You mean the possibility to use a see-through HMD instead of the normal HMD?
Mm-hmm.
Yeah. So it's a we can use a see-through HMD. So.
No. The question is whether the capturing and the lenses that you have could be embedded inside an HMD to kind of watch the reaction of the inside the face while it's covered.
So do you mean the to use do you mean the using the see-through HMD to see the avatar, the face?
The face of the person who wears the HMD. So one of the one of the potentials of this use of lenses and cameras is to transfer the information to another spot. So you don't have to put a camera looking at the people directly. You can put the camera somewhere else.
So let me see. So yeah, I think we can make it. So, yeah, but
You don't
so
think it?
far, yeah. So far as I don't know. So
Okay,
yeah.
that's good. That's good. Don't worry.
Yeah.
Okay. Do we have any more questions here? Anyone from the other speakers has any questions also, or? Okay, I guess we can move on. Thank you very much, Kay. It's super interesting applications also. And yeah, all your validation is very thorough. So I can imagine a lot of people will use it for reference also. Okay, thank you.
Thank you.
Okay, we continue with the session 4, Avatar Perception. The next speaker is Andrew Best from University North Carolina, Chapel Hill. And he will be presenting SPA verbal interactions between agents and avatars in shared virtual environments using propositional planning. Okay, thank you, Andrew. And just one more thing, remember you can send your questions through Slido at any moment. Thank you.
So thank you very much. My name is Andrew Best. I'm a research scientist now with Toyota Research Institute, but this work is done as part of my dissertation at the University of North Carolina, along with my co-authors Sahil Narang and Dinesh Manocha. And today I'll be talking to you about Sense Plan Ask, or SPA, which is a method for enabling verbal interactions between agents and avatars in shared virtual environments using propositional planning. So just a brief outline, I'll discuss some motivation, the goal of our work, discuss prior approaches, give you some details on our approach, discuss our results, and offer conclusions. So the motivation for this work is interactions in VR. So we're finding VR technology is increasingly ubiquitous. We see rapid increases in the available games, available consumer headsets, and the research being done in VR. But interaction remains an open problem. So often we find virtual characters, I'll refer to them as agents, lack interactive capacity in VR applications. Or human characters, we'll refer to them as avatars, can interact, but those interactions don't always feel natural. It's unfortunate on the virtual character front because we've seen that virtual characters benefit a variety of interactive applications. We've seen them used for training simulations, for treating social phobias, for increasing the sense of quality in social VR. And it's important because those agents can interact with the avatar of the user, right? That digital representation directly, and can really increase the quality that a user perceives from a virtual environment. We also know, as actually was mentioned in prior talks, as the quality of animation improves and the quality of visual fidelity improves, the quality of the behavior must improve. Otherwise, you'll actually reduce the user's sense of quality of the virtual environment and the experience. So what we find right now is that in VR, virtual agents may not always feel interactive. Even if they're noticing you, they're navigating around you, they don't always appear to recognize that you're there. Or sometimes they do recognize that you're there, but they don't do so in a natural way. So maybe their gaze behavior or their attention behaviors are not as natural as they could be. So the goal of our work is to propose a different interaction mechanism, right? So to improve interactions between agents and avatars by leveraging verbal interactions. So our primary goals are to generate plausible virtual agent behaviors, to generate verbal interactions between human avatars and virtual agents, to generate verbal interactions between those virtual agents themselves so they can communicate with one another, and to create proactive interactive agents. So we don't want the agents just to respond to interaction, we want them to seek it out as well. So to dive into detail a little bit on that, we want not just locomotion, we want verbal actions and interactions between avatars and agents. And again, we want those agents to respond to both avatars and agents. These agents are going to seek out interaction. So we're going to imbue them with explainable goals so that they can ask questions about what they're trying to accomplish or provide information. And of course, we want those to be plausible behaviors and operate at interactive simulation rates. So we want to be able to support multiple agents that can ask questions and provide answers all at VR rates. There's prior work in the area of agent-avatar interactions, of course, and agent-agent interactions, but the prior work tends to focus on very limited interaction scenarios. So you've either got one or a very small number of agents interacting with the avatar, and generally the agents are treated as implicit collaborators. So this means that they don't have their own goals. They exist to facilitate the user's interaction in the environment or to facilitate the goal of the user. And then in crowd simulation, when you get enough agents or many agents, they tend to limit the interactions to nonverbal interactions or just collision avoidance. There's other work in agent-agent interactions, of course. So in crowd simulation and other fields, these tend to rely on message passing. So you don't actually have verbal communication as the produced signal. They do an offline process, they pass messages around, and then we post-process and generate the verbal interactions after the fact. It's also true that these interactions typically have to be pre-scripted because with large multi-agent simulation, we tend to use rigid structures like finite state machines or behavior trees, which limit our ability to give the agents explainable goals and the ability to replan. So that's the prior work. Now I'd like to discuss our approach to addressing this problem. So our contribution is Sense, Plan, Ask, or SPA for short. And the major theme is proactive interactive agents. So SPA is an algorithmic pipeline that enables the agents to plan explainable high-level goals under uncertainty. We classify the agents as belief, desire, intention agents. So the agents have a set of things they believe to be true, a set of desires to accomplish, and their intended plans. This is opposed to just point goals like you typically see in large multi-agent simulators. And we want to enable the agents to communicate in natural language. So the agent should seek out information from other agents and avatars and be able to engage in simple question-answer dialogues. And then, of course, this is an interactive approach for virtual agents and avatars to share these environments. So the agents can plan and respond to other agents, but also avatars, all using verbal communication. This is a high-level view of the algorithm. We'll go into everything in detail, but the takeaway from this slide is that we're coupling natural language processing and knowledge-driven propositional planning to generate interactive communicative agents. So let's dive in. To help facilitate the conversation on how our method works, I want to use a motivating example. This is one of the scenarios that you'll see later. This is the finding a statue in an art gallery. So you can see on the right, I have a diagram of this virtual gallery we've laid out. In each of the galleries, there's a statue the agents might want to visit. So I've highlighted the Venus de Milo and the Thinker. These agents have the ability to move, communicate, or visit a statue. That is, they observe the statue. And what's important here is that we don't necessarily tell the agent where the statue they're looking for is. So we tell them they want to visit a statue, but we don't necessarily give them that information. So they have to go out and seek that information from other agents and avatars. To set up these scenarios, we use an environment description model and a lexicon. And these are stored for an implementation detail in YAML. But what they tell us is what are all the objects in the scene? What are all the actions the agents can take? And these are propositional actions I'll get to in a moment. And what are those initial conditions of the agents? So where are all the agents and all the entities? What do the agents want to accomplish? And what do they know? And I'll describe the knowledge understanding in a moment. The lexicon itself is just an example set of sentences we use to train the NLP system. In the interest of time, I won't go into all the details on how we train the parser, but you can find that in our paper. But suffice it to say, the lexicon has a set of templates. So for example, what is the location of entity statue, right? So this can be substituted for any entity in the scene as long as the entity meets the criteria of being a statue. So what is the location of the Venus de Milo, for example? Where is entity gallery would be, you can ask about anything that is a gallery. So we substitute these templates in and we train the parser using that set of sentences. Our agent state is represented in a fairly typical fashion. We have the physical state of the agents, so the position, velocity, what action they're engaging in. But we also have the behavior state, so what they know, what they're trying to achieve, and their current plan to achieve that. And then we link that into a set of action controllers. So these are hierarchical finite state machines that allow the agents to engage in sequential behaviors as part of a particular action. The knowledge itself is represented as a set of entities, so objects or concepts in the environment, and relationships over those entities. We encode them as strips like predicates. So this is a set of first-order formula over the entities in the scene. We also include attributes for the entities. So we can say something is a statue, but we can also say that maybe it's a marble statue. We define a set of actions, and these actions are given a set of preconditions. The following postconditions will become true if the agent takes this action. And again, for the interest of time, I can't go into full details, but you can find more information about this in our paper, or the propositional planning literature is quite good. And then we encode this knowledge as well at runtime in SQL so that we can perform quick queries over the database. So just to give you an example, consider the gallery where we're operating. We've got this statue, the Venus de Milo, and we know it's made of marble. We have the notion that there is some gallery, we'll call it Gallery A. And perhaps we know that the location of the Venus de Milo is in Gallery A. So that's an example of what the propositional predicates look like. And then we give the agent a desire that visited the Venus de Milo is true. So the agent will have visited the Venus de Milo for this to be considered successful. To leverage that knowledge, the agents create plans using a novel propositional planner where we enable them to plan with uncertain information. So we take a different approach to uncertainty planning. We allow the agents to plan in 2 stages. So the first step is that the agent will build a plan template without resolving any uncertain information. The agent then plans actions to resolve that uncertainty. So once we have the uncertain plan, we start inserting questions or exploration. And then we replan for the agent anytime new knowledge invalidates that plan. So that looks something like this. Consider that the agent wants to visit the Venus de Milo, but doesn't know the location. The agent can make a plan that says, go to Gallery X, where X is a variable. We don't know the answer yet. And then we want to visit it. Now, the only thing we know about X is that X has to be a predicate an entity such that location Venus de Milo X is satisfied. Now the agent has an incomplete plan with uncertain information, but it has a plan to start with. And now we can augment that plan with verbal interactions to resolve the uncertainty in the plan. We do that through natural language interactions. So in the interest of time, I won't go into full details on the parser, again, available in the paper. But we use a shallow semantic parser. In particular, we're using the Rasa NLP parser. And shallow semantic parsing is designed to take an input sentence and assign it some intention, some intent. So what is the user trying to get across when they're speaking? And then to pick out hot words or named entities. So we train the parser very simply on four intents, either predicate questions, predicate answers, attribute questions, or attribute answers. And then when the agents need to produce language, we can use template matching in the lexicon. So they go back to the lexicon, they look up what they're looking for, and then they're able to produce natural language. And of course, the agents hear all nearby natural language utterances just based on distance. The attention model is quite simple. So an example of that, we have this candidate X. So perhaps we'll assume it's Gallery A. The agent will produce a question that says, is the Venus de Milo in Gallery A? If a nearby agent answers no, that new knowledge invalidates the plan. A new plan candidate is chosen such that X is now Gallery B, and the agent can continue planning. That's the overview of the algorithm. That's how it works. And now I'd like to detail some of the results we were able to generate using our approach. So first, we conducted a within subjects online user study. We compared SPA against 2 other methods. So one called no communication, where we have agents that cannot interact using natural language, and one called no agents. So we just have environments with no agents, and that serves as a baseline. The metrics that we were interested in are things like the plausibility of interaction, the plausibility of the simulation, the impact of the natural language interaction, and the quality of that, the impact of the quality of that interaction. To actually perform the study, we recorded interactions with 3 confederates. So we recruited three local participants. We sent them in the system. We didn't train them on it. We just let them interact with it. Each of them was asked to navigate 2 environments. So they were given a task to find a specific artifact, so a statue, for example. And in the case of SPA, the agents were able to provide assistance if the participant asked and asked for information. Our online participants, as opposed to our confederates, compared these videos side by side in a paired comparison fashion and indicated their preference between SPA or the other method. Here's an overview of what these testing environments look like. So on the left, you see the virtual gallery, and on the right, you see the virtual trade show. And I'll show you just a brief sample of what these interactions look like. So on the left is no communication, and on the right is SPA.
Okay, let's go find that statue. Hello, where is Lucy located?
Gallery F is the location of Lucy.
Great. Thank you.
What is the location of the thinker?
The thinker is located in Gallery A.
Thank you.
No problem.
So that gives you an example of the environments themselves. And I'll discuss some of the results we found. Overall, we find that the presence and quality of natural language interactions provides a positive impact over other methods. So users tend to prefer agents that can interact over agents that could not. And we also find that users felt that, or excuse me, participants felt that the simulations more closely reflected real world scenarios and generated more plausible interactions. And what's important there is if the quality of the interactions was sufficiently low, as we've seen in prior research, that would have actually caused a degradation in their perception. So our interactions are sufficiently plausible that the users felt that they provided an improvement to the virtual environment. We also wanted to conduct timing evaluations, and I can refer you to the paper for details on the other benchmarks we performed, but I'll briefly discuss the complexity of the planning problem and how that scales. So consistent with other prior propositional planning approaches, the initial planning scales exponentially in the size of the problem domain. So the x-axis here is the size of the information domain. That means the number of predicates that could be true. And we do find that that exponential curve starts to grow as the number of predicates increases. But using the two-stage planning approach, the average replanning time remains quite low, even when you have complex information domains. So we can perform initial planning offline, perhaps, and optimize that way. Replanning is very quick. We're leveraging this work and prior work that we've done in avatar capture and avatar gate capture to move towards these behaviorally rich multi-agent environments for shared virtual experiences, like the one detailed below.
Okay, agent. Where is Waldo?
I'm sorry, I don't know.
Okay, who does know Waldo's location?
Max may know Waldo's location.
Helpful. Where is Max? All right. Are you Max?
Yes.
Good. Max, where is Waldo?
Waldo is behind that gate.
How convenient. A gate. Nope. We need a key. All right, maybe we can... Let's see. So... Max, do you have a key?
Yes.
So that's just an example of the kind of work that we're moving towards, combining the work that we're doing here. So to conclude, I've demonstrated SensePlan Ask, which is a method for improving the sense of realism and interactions in virtual environments. It generates plausible natural language interactions between agents and avatars. We have proactive agents, so they seek out information and they learn from those interactions. They can accomplish high-level goals in uncertain environments, so they're not just moving point to point. They're doing something that they can describe, and we facilitate agent-avatar interactions. There are clearly limitations in the work. First, the performance is exponential in the size of the problem domain, so we can replan fast, but that initial planning is very expensive. Our small lexicons enable us to train the parser with very few examples, but it does mean that the agents are limited in their conversational ability outside of the question answer. And domain configuration can become difficult considering the size and number of entities. So the more things that could be true, the harder it is to write up a configuration file. In the future, we can explore other ways of dealing with the planning problem. So there's partial order planning and alternative planning approaches that might enable us to plan more quickly. We could also leverage online systems for conversational engagement. So if we detect a question that's outside of our domains, we know that the intention is not one of ours, we can offload that to a conversation agent. And then, of course, we'd like to perform a more detailed study where the participants themselves interact directly with the system rather than observing confederates interacting with it. So just quick acknowledgements. I'd like to thank my co-authors, Sahil Narang and Dinesh Vanusha, and of course our funders who helped us do this work. So thanks very much for your attention, and I can take questions now.
Okay, thank you very much. Everyone who wants can submit questions on Slido. I have some questions.
Sure.
Generally, when you have this type of experiences, you have a plot, right? You need this person to go here and do this, or like this series of things. What if they don't? You know, like, do you have any idea of how you can advance the plot if the person does not ask the right question.
That's quite interesting. Yeah, so the use of agents with a knowledge base doesn't preclude story-driven advancement, right? So not every agent has to be using this basic interaction system. So if the user's not doing well, you can always use a scripted agent to come in and you know provide the suggestions, right? In general, though, the question and answer works fairly well with anything in the domain. So even if the user's asking the wrong questions, they're still getting information from the agents. So they might ask about a statue that no one cares about, but they'll still get, you know, that statue is made of stone, but that may not help them.
Yeah, I can imagine that if you have a story that needs to follow, at some point they're asking what the material this statue is, it might not be so advancing the plot. And I think there is a need to constrain. Like if you are designing a game with a plot, you don't want every possible solution to happen. You want to constrain it. And I guess if you have very smart agents, people could go anywhere and then nobody's playing the same game.
So that is interesting. You're right. The only thing I would say to that is before the days of the visual MMO that we live in now, there was the MUD, right? The multi-user dungeon where everything was text-based and really any possibility would be presented. The user could say, you know, look around, and they would get information about a bunch of stuff that didn't matter. And the responsibility of advancing the plot was put on the user. So I think it reflects a different kind of storytelling, right? So you have some stories that you really want to tell through a guided plot. But I think methods like this, you know, if they're improved and made more robust, could be used to tell stories that maybe don't necessarily have a strict plot. And I think that that's an interesting method of storytelling as well.
Yeah, okay. That sounds good and reasonable. And yeah, do we have more questions? No more questions at the moment, but you know, at the end of all the talks, maybe if you guys can join the Mozilla Hubs, and I think more people will come and do questions there. Okay, let's get ready for the next presentation.
Thank you.
Okay, thank you. We're back again in session 4 Avatar Perception, and we have the last talk right now by Shishir Subramanian from the Centrum Wiskunde and Informatica. And he's going to be presenting the work on comparing the quality of highly realistic digital humans in 3D of and 6D of volumetric video case study. And of course, as with every talk, if you have questions, please send them on Slido and we'll gather them at the end. Thank you, Shishir.
Hi, welcome everyone. Today I'm presenting our paper comparing the quality of digital humans in 3 degrees of freedom or 3DOF and 6 degrees of freedom or 6DOF, a volumetric video case study. Let me start by telling you what I mean by 3DOF and 6DOF. So a popular format used in VR experiences is the 360-degree video, where the user is placed at the center of a spherical video. The user is then allowed to make head movements to look at different parts of the sphere, but the user cannot move within the scene. He is fixed to the location of the camera, and we refer to this situation as 3DOF. An extension of this is constrained 6DOF, where the user is presented with multiple such spherical images taken from fixed locations. The user can then navigate to one of these fixed locations and inspect the content using head movements. But if you want to deliver experiences to users where they're able to freely navigate within the scene and allow them to rotate and translate their viewport freely within the scene, we need to represent objects in the scene using 3D models and volumetric signals. In this work, we consider this problem, this class of applications where humans are represented using such 3D models and volumetric signals. So the context of this study is social VR, which is a system that invites multiple users to meet and interact in a shared virtual space. It has been shown in previous research that realistic human representations in VR lead to a better sense of social presence. So in the last decade, this class of VR applications has gained greater commercial popularity. This is thanks to the availability of new and affordable head-mounted displays with position tracking, 360-degree cameras, depth sensors, as well as new content. The experience of wearing a head-mounted display is immersive, but also at the same time, one of isolation. So the recent trend in VR applications is to create a multiplayer scenario. So VR for social interactions, which allow live communication, telepresence, and so on. And this is what we call social VR. SVR requires volumetric user representations, so volumetric signals. And it also implies that the user can freely move in the virtual space while interacting with content as well as with other users. One approach is to use avatars as done in applications like Facebook Spaces. And the focus here would be to make the avatars realistic, expressive, interactive, and autonomous. Another approach is to use photorealistic volumetric reconstructions of the users. So this would allow the users to interact in the virtual world as themselves. It creates a feeling amongst users of cohabiting the same space and allows for more natural interactions. But this also requires a large amount of data, and due to these requirements, the research problem is not so much about how to render and animate these representations, but about how to transport them efficiently. So the popular formats that are used to create such reconstructions are an animated 3D mesh. So this is created by reconstructing the user as a mesh and then recording their movements through motion tracking. And a new popular format for such reconstructions is the 3D point cloud. So as you can see here, it's a dense point cloud of about 1 million points. It provides a photorealistic reconstruction. And as I zoomed in there, you can see that the model is essentially a collection of rendering primitives presented as points. So a point cloud is a collection of points in 3D space that have X, Y, and Z coordinates representing the geometry and additional attributes stored at every point. This could include color, transparency, material properties, surface normals. There are no restrictions on what attributes can be encoded at each point. This format is also resilient to noise and requires no additional pre-processing, such as the triangulation that is needed to generate mesh topology. This makes point clouds suitable for real-time reconstructions. But point clouds require a large amount of bandwidth and storage space. So compression is essential in order to stream them over bandwidth limited networks. So there is a need to understand how to evaluate the perceived quality of decompressed point clouds in order to design and optimize these codecs. Point cloud compression has received significant research interest in recent years, including a standardization activity launched by the standards body MPEG, and they're expected to announce a new standard later this year as well. So in this study, we consider two point cloud codecs, the MPEG Anchor codec that was used in the call for proposals for developing the standard, and the current version of the upcoming MPEG VPCC standard that is release 7.0. So in this work, we evaluate the quality of compressed dynamic point clouds of digital humans using these two codecs. And to our knowledge, this is the first evaluation of dynamic point cloud sequences conducted in an immersive environment. Previous work has used 2D videos or has evaluated static point clouds or single frames. We provide quantitative subjective results about the perceived quality. We also provide qualitative insights on what is important to users interacting with digital humans in VR. We performed this study in two viewing conditions, 3DOF, where the user was sitting on a swivel chair. They were only allowed to make head movements from the chair. And in 6DOF, where the participants were free to walk around the virtual room while inspecting the point cloud digital humans. Let me now tell you a bit about how we set up this experiment. So to create the dataset, we use the point cloud dataset shared by the MPEG standardization activity. And we also created our own point cloud sequences. So to do this, we created 4 sequences by sampling points from the surface of an animated mesh. The points were sampled with a probability proportional to the area of the face on the mesh surface. And we sampled about 1 million points for each frame to be consistent across the data set. So here you can see on the left, this was a frame from the animated mesh, and this is the resulting point cloud with points sampled from the surface. So this is the entire data set that we used. So on the left here, we have the data set of sampled point clouds. So that's Manfred, Sarge, Despina, and Queen. The 4 on the right here are from the 8i dataset shared during the MPEG standardization activity. And these sequences were captured using photogrammetry, using an array of 40 plus cameras around the subject being recorded. So these sequences are long dress, loot, red and black, and soldier. So this data set, however, was too large for us to ensure smooth, consistent playback. So we split the test into two. T1 considers the sampled point clouds, the 4 on the left here, and T2 considers the reconstructed point clouds, the 4 on the right. So all the sequences were clipped to 5 seconds, and they were rendered consistently at 30 frames per second in the Unity game engine. As I mentioned, we considered 2 codecs for the study. We compressed the sequences to 4 target bit rates. This was based on the common test conditions and compression profiles shared by MPEG. And we achieved these target bit rates with both codecs. The rates roughly varied from 4 to 140 mbit per second. And in each of the tests, T1 and T2, the participants viewed 32 compressed point clouds and 4 hidden references, 1 for each sequence. So to do the test, we recruited 52 participants. 27 took part in T1, 25 took part in T2. As I mentioned, the participants viewed the content in 2 viewing conditions, so 3DOF on the right and 6DOF on the left. And the sequence of these 2 conditions was also randomized to avoid any influence. So the user on the left is in 6DOF. She is free to walk around the room while inspecting the point cloud object. And the user on the right is in 3DOF. He is confined to the swivel chair for the test. So before starting the test, the participants were screened for visual acuity and color vision. We performed this evaluation with a single stimulus absolute category rating with hidden references methodology. Participants were asked to evaluate each sequence on a 5-point scale, with 1 being bad, 2 for poor, 3 is fair, 4 is good, and 5 is excellent. Before starting, the participants were shown 3 training examples of the scores 1, 3, and 5. And this was done using additional content that was not used in the test itself. And during the test, participants were first shown 2 dummy sequences to sort of ease them into the task. And the scores for these were discarded from the analysis. After the test, we also conducted an interview where we asked participants about the factors that they considered during the evaluation, if they faced any difficulties in the assessment, and their comparison between the 2 viewing conditions. Now, let me tell you a bit about our results. This is a score graph for one dataset, the one sequence, Sarge, in 3 degrees of freedom. The solid line here represents the mean opinion score. The dotted line is a differential mean opinion score calculated based on ITU recommendations. The flat yellow line represents the average score given to the hidden reference, so the uncompressed original sequence. The blue line represents the VPCC codec. The orange line represents the MPEG anchor codec. And you can see that we have 4 rate points, R1, R2, R3, and R4 with their confidence intervals. So this is all the results for T1 in both 3DOF and 6DOF. So we can see that for the first 3 sequences, Sarge, Despina, and Manfred, that VPCC is generally preferred over the anchor codec, especially at the lower bit rates. At high bit rates, the codecs are statistically equivalent. In the case of the last sequence, Queen, we see that the hidden reference was assigned the low score of 3.3 in both viewing conditions. This means that the original uncompressed sequence was not considered high quality by the participants. And this results in a much smaller rating range across the 4 rate points. And about 27% of the participants expressed dislike for this sequence because of the lifeless appearance, the slow movements, and the static gestures. The mean opinion score given to this sequence Queen only vary from 1 to 3.35 in 6DOF and 1 and 2.58 in 3DOF. We can see that the bit rate points R3 and R4 are statistically equivalent, and even R2 and R4 are equivalent, and the difference between these is 10 times the bandwidth. And in general, in the 3DOF case, transparent quality, that means the R4 decompressed point cloud being given the same score as the uncompressed original is only achieved by Manfred at R4. Moving on to test 2, we can see again that there's a variability between the different sequences used in the test. At high bit rates, the long dress and red and black sequences are consistently given lower scores in both viewing conditions. Even the hidden reference is given lower scores. And they don't reach MOS levels higher than 4. So for these two sequences, we see that they have a smaller rating range. We also see that they seem to achieve transparent quality at the higher rate points, R4. And we found that the scores are statistically equivalent to the hidden reference. About 48% of the participants mentioned that their quality assessment criteria are content related. They reported that it's easier to spot artifacts for content with complex patterns like long dress, as well as dominant colors like red and black. For the second pair of sequences, loot and soldier, we see that the hidden reference was given a higher score and that they utilize the full rating space across the different rate points. We see that both codecs are not able to achieve transparent quality at high bit rates. Participants also reported that they preferred the soldier sequence, the last one here, due to its high resolution facial features, unitone clothes, and natural movements. So to summarize the results, we see that in both T1 and T2, VPCC is preferred over the MPEG anchor at lower bit rates, while at higher bit rates, their performance is comparable. The MPEG anchor codec is based on octrees, so it represents 3D point cloud geometry using octree occupancy. This style of codec design allows for low delay encoding and decoding, and it makes it suitable for real-time applications. VPCC, however, is based on projecting the point cloud to 2D and then using legacy video codecs to encode the geometry as well as the colors. This type of codec design has a high delay encode, but it also allows for low delay decoding, especially because it's using these video coders, so we can leverage hardware acceleration on modern GPUs, making this suitable for on-demand streaming. We also found that for the content we considered in this test, a bit rate of 20 to 40 mbits per second is required to provide acceptable quality. The two viewing conditions that we considered lead to similar trends in scores, but there is a trade-off here. The 3 degrees of freedom case offers a more stable testing environment as the participants view the content from similar viewports, and they're also at the same distance from the digital human. In 6 degrees of freedom, it's a more realistic testing environment. Participants reported that it felt more natural, but it could vary from participant to participant as they're free to move around in the scene. So from this evaluation, we find that there is a need for a larger body of point cloud digital humans compiled using various acquisition techniques. This is needed to design, optimize, and test the point cloud compression solutions of the future. In our test, we see this in the difference of the results between T1 and T2. The performance gains achieved by VPCC vary considerably when new content is evaluated. Another thing we saw was that content preference has a significant impact on ratings. Future work in such quality evaluations may need to be adjusted based on the content and viewing preferences, and they should offer training with a broad selection of content. During the interview, participants reported that the factors that they used to assign quality were things like the overall outline, pattern distortion on the body and clothes, the naturalness of the gestures and movements of the digital humans, as well as visual artifacts such as blockiness, blur, and extraneous floating artifacts that are introduced by compression. We also see that current point cloud codecs, although efficient at lower bit rates, are unable to provide visually lossless compression, even at very high bit rates like 140 mbits. So in future, we plan to perform a comparative study with state-of-the-art objective distortion metrics as well. We will conduct a subjective study using 2D videos like previous research with fixed navigation patterns around the object and then creating these videos to evaluate codec performance. We will also study live point clouds that are captured in real time using 4 commercial depth sensors. That concludes my talk. Thank you for listening.
Thank you very much, Shishir. Like before, everyone who has a question, please add it to the Slido. We have one question here by Gregor Dupont. How do you render the point clouds in Unity, existing tool or custom code, or that you develop?
It's a custom code. It's based on a vertex buffer, and a primitive is rendered at each point. And we use
Okay.
the same size for the primitives.
Good. Gregory has a follow-up, because if it's custom, do you plan to make it available for the use of others?
I think so, yes. So this research is funded by an EU project, so we will be sharing all of our results.
Okay, so I will just direct you to talk to Shishir offline also, and maybe you can get ahead of the tool. I think Mozilla Hubs is probably a good place to do that. Okay, let's see if there are some more questions here. Yeah, I have one question regarding codecs, because it kind of feels that we're reusing codecs that were not meant to be used for volumetric information. Do you think it's about time we think of completely new codecs that are
I
meant
agree.
for point clouds?
Definitely, I think so. I think codecs should be based in the 3D domain, and they should be optimized for human perception in 3D.
Yeah,
This VPCC codec, they wanted to go quick to market, and the advantages of hardware acceleration are hard to ignore.
Yeah, I'm seeing this also in other conference, like the multimedia conference. A lot of people comparing codecs. How well do they work in here? I'm like, maybe we should just do a complete new codec for volumetric point clouds.
Yeah.
Okay, let's see. I think that's all from the. No, we have one more. Andrew Best from Toyota. Do you intend to test live point cloud capture with multiple devices? Many point cloud captures I've seen only capture in one direction. Do you believe this is a major factor in point cloud versus mesh comparisons?
I think we can use sensor fusion and multiple depth sensors to create a live capture from different directions and create a complete object. And I think there's a trade-off between meshes and point clouds. Point clouds are really good for complex surfaces, and they're really good for real-time capture.
Yeah, yeah. I guess they will coexist, both of them.
Yeah.
Yeah, maybe for object identification, I kind of feel like still meshes are on top of points, right? So you're starting from points and then you put them together through meshes. So they are two things that one is like meta information on the other one, probably, or you could structure them and have the good things from both, right?
Yeah.
Okay, let's finalize our session today. With very good presentations and talk. I would invite everyone here to move Mozilla Hubs now, also the speakers, to hang out there. You can meet with other people who are interested on your work, and also you can go around and watch the poster sessions that are going on there, and people are presenting their posters. I think it's very cool. So yeah, with that, we're done with our session. Thank you very much for your work and for being here.